So in this chapter, Chapter 5, Section B, we're going to look at resistors, capacitors, and inductors. So RC and then RL circuits. So what we're going to look at first is some of the outputs that can be expected from resistors and the calculations, including current, voltage, power, and also how we can use inductors and capacitors in more complex circuits, DC circuits versus AC circuits. So with that ado, let's start. So here we have our picture of capacitors, which we've introduced previously, but again, to reiterate, capacitors are passive elements that store energy in an electric field. So this electric field is defined by the geometry, actually, of the capacitor. If we go over to the parallel plate capacitor, which is the easiest one to understand, and also the one we've had in physics, we have C equals EA over D, where capacitance is a function of the dielectric constant times the area divided by the distance between the two. And so whenever we're trying to create capacitors, a lot of them are based on large areas and small distances between the two. Because, again, that's going to make your largest amount of capacitance. So there's many capacitors with paper that's rolled up really tightly. There's capacitors made with mica, which is a mineral. Actually, if you go out in Fairmount Park, you know all of the shiny rocks that are sitting around. That's wissahick and schist. And schist is a type of mica. So actually, they make giant capacitors with mica. That's one of the ways that you can do it naturally and cheaply. So if we go back to the left side here, we have the symbol for capacitor, which is two parallel lines next to each other with positive and a negative. You have a voltage drop between the two. We have I equals C dV dt, so the current equals the capacitance times the change in voltage over the change in time. And if we go down a little bit more, we have the equation for voltage too, where voltage equals 1 over the capacitance from T0 to T times the current plus the initial V of T. So also we have if you look above, I skipped it, the Q equals CV, charge equals capacitance times voltage. If we go down below, we're going to get our power equation, P equals CV, and then also we're going to be looking at W equals 1/2 CV squared. So another interesting thing about capacitors is that in DC circuits, capacitors look like open circuits, and we're going to look at why that is. For long-term analysis, they look like open circuits. It's only in short-term analysis where they might not look like open circuits. Essentially, it's because the capacitor is charging up. Once the capacitor is charged, current can't flow through it. So once you leave a capacitor in a circuit, it charges up for a couple minutes, then essentially no more current is going to flow through that after the capacitor is at 100% charge. But things can be a little different around zero, or especially with alternating current, things can be very different. Because essentially you never have time for it to fill the whole way up, or as long as you've sized your capacitor right. So underneath that, we have the voltage on a capacitor must be continuous. You can't have a rep changing in voltage, which is what I was just saying. Because if you change voltage, then essentially your capacitor is going to go through a period of charging and decharging, and that's going to be a function of the resistance, which is the RC circuit that we're going to look at. So on the right-hand side, you see a really quick diagram of what a capacitor looks like. So this is a parallel plate capacitor. Again, the equation C equals dielectric constant times the area over the distance. And you can see what that looks like in a graphic diagram. And that's going to be due to the state of charge that's going to build up on the top, and it's going to induce a charge, Q minus, in the bottom. And that's going to allow, essentially for a brief period of time, charge to flow through the circuit. But if that top plate is fully charged and the bottom plate is fully charged as well, then you don't have any flux going in between, and that's going to create an open circuit, which is why we said in DC it's going to look like an open circuit. So, let's continue on. Various other types of capacitors aside for the parallel plate capacitors shown on the previous slide. And we have coaxial capacitors, where the dielectric material is wrapped around a conductor. There's multiple types like this. We have mica capacitors, which is the type I was talking about before, where you have a metal foil, a layer of metal foil, and a layer of mica, which is that shiny mineral that's outside wissahick and schist all around Fairmount Park. And you just keep layering that up, because every time you layer that, you're going to increase your surface area. So underneath that, we have plastic foil capacitors, which are also super cheap capacitors, where they do an outer foil, and then an inner plastic, then an inner foil, and then another plastic, and they just roll them up. And the rolling of the capacitors keeps a high surface area, to a low density, and that keeps us from getting really large, chunky capacitors, because in general, as capacitors increase capacitance, they also become larger physically because that area needs to grow. On the right-hand side, we see some more exotic capacitors, conductive plate capacitors, where you have a plate surrounded by another plate on the outside, and you can induce charge from one plate to the other. And then underneath that, we have adjacent plates capacitors, or perturbation field capacitors. So generally, these are not used in traditional electrical design. They're more used for sensors and for very specialized electrical equipment, or if you're trying to do special scientific experiments on something. Generally, these we don't use in consumer electronics, just because if you're trying just for a normal capacitor, there's cheaper ways to do it that take up less area, because your area here is going to be growing significantly larger, and you're not going to get nearly as much charge on those plates. We also have capacitors and other types of sensors. Here we have a quick one of a fingerprint imager, where you can look at the fingerprint at the top. You have the sensor in B1. And essentially what this does is this detects the distance between the valleys and the ridges on your fingerprint, because essentially you have a changing distance there. You have a changing capacitance in between those as well, because if you remember from the parallel plates equation, you've got what C equals the permeability constant times the area divided by the distance. So the distance, as it changes, as long as everything else stays the same, you can change your capacitance. And essentially that's what this sensor does, is pull out the changing capacitance. Now, another interesting use of capacitors is in supercapacitors. And so supercapacitors are very interesting because essentially they can have large, high energy densities. Right now, our best supercapacitors are around 15% of a battery. They're very large space-wise, but supercapacitors have a couple really great positives. So every time you use a battery, essentially a battery in a car is a chemical reaction that it can essentially recharge itself, but it never recharges itself 100% back to where it was. So as you use batteries, car batteries, lithium batteries, whatever rechargeable batteries you're using, every time you charge and discharge them, you're causing a little bit of damage to that battery, a little wear, and the battery has a little memory, depending on the type of battery. Cadmium batteries have worse than that, but depending on the battery, you have a little bit of damage done every time to it. Capacitors, while they can't hold as much, they're 90% weaker, 85% weaker than normal batteries for the same amount of space. They have the ability to never, essentially not really be damaged. You can charge and discharge them hundreds of thousands of times without them losing any quality in their battery storage. Then the other even cooler thing is that supercapacitors can charge in extremely fast time. So if you look on this diagram here, we can see that lead acid, nickel cadmium, or lithium ion batteries have a relatively high energy density, but they also take a very large amount of time to charge, around an hour or so. Fuel cells take even more amount of time to charge, but they also have a higher density. They're also much more expensive. So if we look down below, though, we see this big red box of supercapacitors. Supercapacitors can charge in less than 36 seconds, some of them down to less than a second, which means you can plug your device in, it charges immediately, you unplug it, and now you've got another maybe hour of whatever device you're trying to use. So the power in supercapacitors is that they're incredibly fast to charge. They can take a lot of charge and discharge cycles with no damage on the battery. And also, they're, in general, much more sustainable than normal batteries, because they're essentially the dielectric material. It's two plates. You can think of it that way, extrapolated into different forms to be able to get higher energy density. But there's no chemicals flowing through there, as opposed to like lead acid batteries. You don't want lead leaching into the environment, so the process for making the lead acid batteries are much worse than making capacitors. So ultimately, we'll probably get to a point someday where our supercapacitors are the way that we charge and use like cars and whatnot, because of just the fast charging time. To be able to plug it in for a minute and have your car charged up is a significant advantage over even the best lithium-ion batteries, which are going to take around an hour, 2 hours, 3 hours, depending. So in this diagram, we have the capacitor response. So if we're given V of t, determine I of t. And we did one of these actually much earlier in chapter, I believe chapter 2. So this is just going to call it back out. So first, what I'm going to look at is given the V of t. So I'm going to look at the top one, which is the change of voltage over time. and I'm going to analyze it. So from negative infinity to 0, we're going to have 0. So of course, if I go that to current, current is going to be 0 as well, because again, the derivative of 0 is 0, so that goes out. So the next bit we're going to look at is that first slant there. And you can see that slant is rising 10 and running 2. So the curve there is 10 divided by 2, which is 5. And if we look at the bottom one, we see that the answer is at 3 and not 5. Why is it at 3, not 5? Well, that's because if you took at the top left corner, we said the capacitance equals 0.6 mu farad. So 0 0.6 times 10 over 5 is going to equal 0 0.6 times 10 divided by 5, 3. So that's how we get the 3 below, essentially, because of the equation that we're given. So if your capacitance was 1, then yes, you'd have the same going across. You could just multiply by 1. But since it's not 1, we have 3. Then we're going to look at, in the top one, when what is this, time 2 to time 4. And you're going to see it's going to flatten out there, the horizontal line, at 10 volts. And that means there's no change versus time. And no change versus time in the derivative means 0. So that's why we're going to have a step function that's going to go back down, a negative impulse function, impulse down, a step down function. That's going to go back to 0 between time 2 and 4. And now if we go back to the top one, we're going to look at the slant coming from between time 4 and 5. So that is going to rise negative 5, and it's going to run 1. So 5 divided by 1 times 0.6 is going to equal minus 3. And that's why we have that unit impulse function down below in the current graph. And if we go back up to the top graph again, from 5 to 7, we're going to have a constant voltage at 5. And because there's no change in voltage over time, then there's no change in current over time because it's a derivative, so we're going to go back to 0. So that's how we kind of calculate out the responses for this given capacitor at this given voltage set. And we can do this with much more complex numbers too. It doesn't have to be just step functions and ramps and slopes. We can also do exponentials, curves, and we're going to look at some of that coming up in the future slides. So here we have RC circuits, or resistor capacitor circuits at DC. And this is going to be an interesting note, but at DC, no currents flow through the capacitors, so we presume they're open circuits. So if we look at this circuit drawn here, and if we're going to do for a large amount of time, so this is going to be after, I don't know, 10 hours this circuit's been on. We're going to look at it, and we're going to determine what happens. So if it's DC, then, and it's been on for a long period of time, our capacitor 1 and capacitor 2 are going to be open circuits. So we can literally, if this was just drawn out of pencil, we could erase C1 and C2 and just leave holes in those circuits. And then we could calculate what's left. And what's left is that circuit going around the outside, the 20 volts, 20 kilo ohm, 30 kilo ohm, 50 kilo ohm, and then back to the return on the 20 volt source. So essentially none of the inside on this matters. And so we can draw it and draw it like this, and this is the simplification at DC for a given amount of time, what this circuit looks like, which is pretty easy. Essentially, we just remove the capacitors. Now, if we want to go back and just clear this up a little bit more, you can see that we leave them open, open test points there, open holes, because it's still open circuits. But there is also something there that we might have to worry about if the source changes to an alternating current, or if we're looking at a very, very quick period of time before the capacitors are charged. So capacitors in series here we're going to look at, and this is essentially showing how we can add capacitors in series. And capacitors in series add the exact opposite as resistors. So remember, resistors in parallel add as capacitors in series. So 1 over the reciprocal, and then add them all up, 1 over the reciprocal, 1 over the reciprocal, up to the minus 1 is going to give you your C equivalent. And that's when the capacitors are in series. So again, capacitors in series equals resistors in parallel, just the way you add them. And we can simplify that with an equivalent circuit, just like we did with resistors. Instead of 3 capacitors, we can add them up into an equivalent circuit, capacitance equivalent, and then we can plug it back in as a single capacitor for simplification of the circuit. If we look at the right, we can use KVL, Kirchhoff's voltage law, the same way to look at the Kirchhoff's voltage law through each capacitor, because Remember, each of these capacitors is on the same, essentially one wire coming in, one wire coming out. So they're all the same current. IS in that top left diagram is the same through each one of these capacitors. Because again, there's nowhere for a current to split. So all current in equals all current out. And so if we derive that and run through it, essentially you're going to get the equation that we're saying, where 1 over C equivalent equals 1 over C1 plus 1 over 2 C2 plus 1 over C3, or however many capacitors you have in the line there. Which again is the mathematical way of proving that capacitors in series add like resistors in parallel. Now, likewise, capacitors in parallel add like resistors in series. And this is very simple to think about because look, if you look at the picture on the top left hand side, remember the area between the capacitors is, in between each capacitor is contributing significantly to the electric field. And so if you're just adding three capacitors in a line, and they're the same dimensions of each capacitor, just say 1 square inch, 1 square inch, 1 square inch, you can see how you're adding those capacitors, the surface area of them, to have 3 square inches. And that's a really easy way that we can use to remember in the future if you ever forget which way capacitors add. To remember that capacitors in parallel add like resistors in series. So capacitors in parallel, you just add them up because it's essentially the surface areas that matter. So if the surface areas matter, 1, 2, 3, then you have 3 as your final capacitance. Again, this is another way of looking at this too, is 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 going to be made into a current divider that's going to go through each one of these pieces. So if we add all of these up, all of these individual currents going up, we can make all of these equivalent capacitances going up, and all the currents going up, we can create one equivalent capacitance, which is going to be the same which is going to have the same source current as the equivalent circuit. So again, if we look on the right, we can use Kirchhoff's current law, with the voltage staying the same across each capacitor, where IS equals I1 plus I2 I3, and then we can substitute in for that for the capacitor equation, because remember, we showed you what the current through a capacitor is. And then we can just add them up, and we can also substitute that back to get capacitance equivalent equals C1 plus C2 plus C3 plus however many capacitors you have in parallel. So this is a really easy way if you're missing a capacitance in lab, which again we don't have as many capacitors as we do resistors, so usually you'll have to be creative in making your capacitors. This is one way you can do to make it. So another thing I want to introduce too is also look at voltage division between resistors, voltage division between capacitors, and see how similar it is. So on the left-hand side, we have Vs, which is our voltage source, and we have two resistors, R1 and R2, which are both withdrawing power from the system. And we can do, if we're trying to find the voltage drop across V1 or the voltage drop across V2, we can use the normal voltage division rules that we have and simplify it out below, where V1 equals R1 over the sum of R1 and R2 times Vs, which is your initial voltage. And we also have the same equation for V2. So essentially, we can use the same model for capacitors as well, where we have a voltage source, and then we have two capacitors with Q1, which is the charge 1 and the minus charge, and charge 2 and the minus charge. And we have a voltage drop over the first and a voltage drop over the second. And so we can also do this for a voltage divider as well, to be able to look at the voltage drop over and in between two capacitors. So we also have another piece of electrical technology at our disposal called inductors. And inductors are shown by this symbol on the left, which is like a squiggly line that swirls down. We have a voltage drop over the inductor. We have current going through the inductor. And inductors we use L to represent, and they're in the unit of henries. So the voltage equals L, which is how many henries the inductor is, times di over dt, or the change in current over the change in time. And if we look over at the picture of the inductor, what's happening is we have a current flowing through an inductor, and that's going to generate a magnetic field in that inductor. And that magnetic field is going to store it's going to store some of our available energy, and that's going to allow us to, in some ways, slow or filter electronics in the future. So if we go back to the left-hand side, we have I equals 1 over L T0 to T times the voltage of T dt plus I T0, the current at the initial time. And so that's going to give us our current output for the inductor. And then below that we have our power, which is Li di dt, and Rw, which is 1/2 Li squared. And so at DC, our inductor looks like a short circuit because essentially all an inductor is a wire that's curled up. And so at DC, it doesn't really matter from our mathematical perspective yet about having how our wires are shaped. Later on, if you're looking at RF electronics or more in detailed signal processing, the way that you shape your circuit board and the wires on your circuit board really does matter if you're trying to pick up signals, because you don't want to have antennas indeliberately in your circuit. However, for DC, our inductors looks like a short circuit after a large sufficient period of time. Also, our current through inductor must be continuous. You can't have abrupt changes in current because that will also mess up our calculations as well. So we're looking at inductors over large periods of time for the short circuit and also having it DC. So here we have a couple different pictures of inductors. We have a high current inductor up above, which is essentially a strip of wire that's been wound around itself a couple of times in order to generate the magnetic field. And remember, if you want to look back through, there's ways, and we'll look at this, I guess, in magnetics too. I think that's chapter 10, where how electric fields are generated by current running through a wire. And we've had some of it in physics too, but it gets more complicated than that. So in the right, we have planar inductors. So planar inductors are also, they use these sometimes for different tracking mechanisms because they're very simple. They're very flat. You can do this with electrically conductive ink. And at the bottom, we have solenoids. With solenoids are a type of inductor that allows maybe a lock to move. So if you go back to the Amtrol lab piece in the electrical engineering lab in HH126, you'll see on that shelf that there is an inductor there and a solenoid inductor. So it has a pin inside of it, and if you flip the switch on while the pin is in, it'll suck the pin into it. And if you flip the switch off, then the pin can come out. But if the switch is on, you're not going to be able to pull that pin out. And likewise, you can do solenoids in reverse to be able to make like coil guns or rail guns to be able to launch a projectile very quickly using a magnetic field. On this slide, we're going to look at the inductor response to a given equation. So our inductor responds to I of t equals 10 e up minus 0.8 t sine pi t divided by 2 for times that are greater than or equal to 0. So if we look at the circuit A, we're going to see our RL circuit, which is what that equation comes down to. So we have a voltage source there, we have a resistor, we have a switch that's going to switch on exactly at t equals 0. I'm going to get to why that's important. And then we're going to, once that switches on, we're going to have the current I of t be able to flow through our inductor. So if we look at picture B, what's going to happen is as soon as we flip that switch, you're going to get current flowing through the circuit. So before the switch is switched, you're going to have nothing, which is why we don't even include anything to the left-hand side of 0 of time. So at before 0 seconds doesn't matter to us. At 0 seconds, the switch is going to flip, and that that inductor, the magnetic field of the inductor, is going to start filling because of the current flowing into it. And that's going to happen and grow all the way up to where you see that 5.09. And that's the current output. So again, we're plotting that equation that we've given in the top, I of t. And if we plot this equation, essentially it's going to fill up to a certain point, and then it's also going to kind of dip down again, and it's going to start, because essentially there's no change in current, and that's what inductors need, is a change in current. So because there's no change, it's going to peak out, and that's going to slowly approach back down to 0. Interestingly, though, it might go beyond 0 in this case, and that means essentially you have this oscillation for a brief period of time before you're going to reach the steady state power. The steady state current, where it's essentially 0 current. So, if this is the equation that we're given, this is also another indication of why it's important to look at inductors and capacitors, RC and RL circuits, at large periods of time. Because large periods of time, a lot of these circuits are going to go out and balance out towards the end, so the inductor is going to act like inductor is going to act like a closed circuit or a short circuit, while a capacitor is going to act like an open circuit. So if we look down and see, we're going to see our output for the voltage. The output of the voltage, again, we can calculate out because V of t equals L di dt. So what is that? It's the derivative. And we can solve out the derivative just with normal calculus that we've done before. And that's going to give us our minus 0.4 sine pi t divided by 2 plus 0.25 pi cosine pi t divided by 2 e up minus 0.8 t. And that voltage is going to be what we're going to plot in C. And so you can see the derivative in action there directly. And now if we go over to power, the equations for power we can look at. And this is going to essentially show that in that pink region we have current increasing. Because essentially more some of the current is being pulled out into those into the inductor. However, once it starts dropping back down, you're going to have a current decreasing because you have a power transfer out of the inductor. And it's going to oscillate a few more times, but each oscillation is going to get closer and closer to zero, so that over time we're going to approach zero for power reasons, and for voltage reasons, and current. Because again, if you take the derivative of zero in current, derivative of zero is still going to be zero in voltage, so you got 0 and 0. So that's an intro into inductor response, and I'll try to solve a couple of these problems out for you on paper so that you can see exactly how they work out and what we're talking about, but I think this is a pretty good introduction to it. So, like we've just done capacitors and resistors in series and parallel, we have to do inductors in series and parallel. So, inductors in series are going to add together just like resistors. And that's kind of because, and we'll look at this later, but the amount of coils in an inductor is going to have an impact on the inductance of that, because essentially more coils, you're going to get more magnetic field. So if you add, and let's just say that L1 has 5 coils, L2 has 5 coils, L3 has 5 coils, you can kind of think of it as 5, 10, 15 coils. I add them together, and my inductance is going to be the sum of those individual inductors. And that's a nice, easy way of doing it in terms, at least, that match resistors. So if we use KVL, again, we have the same current going through all of those individual inductors. So we can use the equation um, for those in order to get our L1, di, ds, dt, and so on and so on. In order to group like terms, we get L1, L2, L3, di, dt, and then we can get our voltage S equals L equivalent di, dt. And then if you want to simplify that a step further, the L equivalent, or total inductance, equals the sum of the individual inductances. Also, we've got inductors in parallel. And inductors in parallel add just like resistors in parallel. So inductors and resistors, for terms of adding them together in order to generate equivalent inductances and equivalent resistances, are very similar. The same math, the same method. So the reason is, in this case, if we look at our picture, our schematic in the top left, we have a voltage source, we have a current IS coming out of that voltage source, and then that current is going to get split into I1, I2, I3, which are going to go through L1, L2, L3. However, if we look at the top of that inductor, we have a giant supernode there where it's all going to be the same voltage. The voltage coming out of the battery is going to be the same as the voltage going through 1, 2, and L1, L2, and L3. And that mathematically allows us to also do the same thing as resistors. So here we have RL circuits at DC, or resistor inductor circuits at direct current. At direct current, no voltage is across the inductors, so we have a short circuit. So if we take this top left circuit, which is interestingly and kind of complex circuit actually, and we look at it at DC over a long period of time, what's going to happen is we can just, instead of having those inductors, we can just erase them and draw individual lines in between them to short circuit it. So in order to do that, we look down at the bottom one, and we've completed, and we've drawn lines over every inductor, and we've made gaps for every capacitor, because again, the capacitors are going to become open circuits over a long period of time. So we're left with this circuit here in the bottom, which we can calculate out, because essentially you have your 24 volt voltage source. It's going to come up through the 4 kilo ohm resistor. It's not going to go to the right because, again, you have an open C2 there, so none of it's going to go to the right. We're going to have it go to the left, though, through that L3, which is going to do nothing because it's a short circuit, all the way through a 2 kilo ohm resistor, through L1 and back down to the return on the battery. And so this becomes very easy to calculate out because I1 is going to be 24 over 2 plus 4 kiloohms, kiloohms, which is going to give us I1 equals 4 milliamps. It's only one loop in this entire circuit. And then we can use our normal voltage to be able to calculate out the node voltage, and node voltage calculated out there is going to be 8 volts. And so we can also look at the amounts of energy stored in C1, C2, L1, L2, and L3 by doing the W equations, or the energy equations that were previously shown. So in capacitor 1, we're going to store 0.32 millijoules of energy, and in capacitor 2, we're going to store 0.128 millijoules of energy. And again, that's because at a long period of time, these capacitors are charged. Once a capacitor is totally charged, it acts as an open circuit so that current can't flow through it anymore. And that's why we can calculate out the energy equations W, because they're fully charged. Now, if you catch this before the capacitor is fully charged, you get some current that can flow through, and you also get some amount of energy stored in the capacitor, but not the maximum amount, which is what we see right here. And finally, these are the basic properties of R, L, and C circuits, and this is probably the most important slide on this page. If we look on the top, we're going to have our current to voltage relationship. If you look at resistors, V equals IR, or I equals V over R, which is the one we've been looking at the entire time. And that can be rearranged into the V of I equation, which is V equals IR. So Ohm's law can be written two different ways. The same way, if you look at an inductor, we can look down the VI equation equals V equals L di dt, but we can also reverse that around in order to find and solve for I, which means taking the integral to get rid of the derivative there. And that way we get I 1 over L, the integral of V dt of I of t. We also can do the same thing for capacitors, where capacitors, which is Ci equals C dV dt, which is something we introduced in Chapter 2. But we can also use that to find the voltage by integrating. If we look at the power, which is the power transfer in, if we go back to our resistors again, power equals I squared R. And we remember power equals VI, or any of the alternatives there. So power I squared R, we can substitute V equals IR to get power equals VI, or power equals voltage times current. Now we can do the same thing with inductors and capacitors, where power in inductor equals P equals Li, the derivative of di dt, and also the power in a capacitor, where power equals the capacitance times the voltage, the derivative of dV over dt. Additionally, we can look at the energy, W, or stored energy. The stored energy in a resistor is 0, because remember, resistors don't take time to happen. As soon as you turn it on, their power goes through the resistor, and the current flows through the resistor, and that's done. There's no changing time for resistors. Because there's no changing time, no energy is stored. However, L and C have both stored energy based upon the individual inductance or the individual capacitance. And those are the two equations for the stored energy. So L and C hold some energy inside of them. And that's for capacitor. That's why supercapacitors are important to us, because they're allowing us to store some of the energy in the capacitor. Inductors allow us to do it as well, but inductors, you'll see why that's not a good method for energy storage in general. Generally, just because we don't get that high energy density. You need large coils, and that takes up more space. And then if we go down below, we see exactly how to add each of these up in series. So adding resistors in series is like adding inductors in series. And it's like adding capacitors in parallel. Same with parallel, resistors and inductors add the same, and capacitors add the opposite. If we expose each of these elements or devices or components to a DC behavior, there's no change in an R circuit for DC to AC. It's the same kind of deal. Essentially, it just creates a resistance which is going to drop your voltage over it. Now, in inductor and capacitor circuits, your DC behavior is different. So, at a large period of time, an inductor in a DC circuit is a short circuit. It just becomes a wire because there's no change in current, so nothing is being stored in that magnetic field. There's no change, and no change means zero storage, zero additional storage. Now, as opposed to the DC behavior of a capacitor, after a capacitor charges, it gets to a point where both of the plates are saturated with charge. And if two things are saturated with charge, there's nothing flowing in between, which is why this is an open circuit. There's no current flowing. Can voltage change instantly? For a resistance, yes. For an inductor, yes. For a capacitor, no. Because the voltage is not going to change for a capacitor instantly, because remember, you have some charge there, and that's going to cause some of that voltage to drop slowly. I mean, it's going to not be immediate. Now, can the current change instantly? On a resistor, yes, of course. Whatever you put through it, it changes immediately to adapt. However, for an inductor, the current does not change instantly because some of that, remember, some of that current is stored in the magnetic field around the inductor. And as soon as you stop stop adding current to that magnetic field immediately, then some of that stored energy in that magnetic field is going to come out as current slowly, and that's not instantaneous by definition. With a capacitor, though, as soon as you stop, that current flow is instantaneously changed as well. So again, this is the most important of the slides. This should be your cheat sheet for a test because, again, it holds all the equations that we need to be able to solve some of these circuits. So we're going to come back to this table multiple times in the near future as we do RL, RC, and then additionally, finally, RCL circuits. That concludes Chapter 5, Section B.